All right, hello again. I've got another video for you ready to go, and this is for Unit 10, Day 2. We're still talking about exponent rules, and we're also going to do the paper folding problem. But before we get to that, I might suggest if you've still got this purple sheet nearby, pull that out. We're still going to be using these same exponent rules today. Maybe also we should start with a warm-up. So yesterday, we did some practice with exponent rules. Here's some trickier questions. I'd like you to take a couple minutes and try these on your own. So pause the video if you're watching this right now and give it a shot. Go ahead, pause it. Do it now. All right, if you are watching this, I'm assuming you've tried both of these and you're ready to see the answers. If you have not tried them, please pause it and don't lie to me and actually try it. Okay, here we go. So yesterday I told you that if you are distributing, you want to make sure you distribute to everything inside. So I'm going to put ones on everything that didn't already have an exponent, because this 3 has to go through to every piece, top and bottom. Okay, so it's going to look like 5 to the third, a to the 6th, because you multiply when you distribute exponents, b to the third, all over, 4 to the third, a to the third, and 7, or sorry, what am I doing? And b, get these, 4 to the third, a to the third, b to the 21st. Okay? Then let's deal with the numbers. 5 cubed, that's 125. And 4 cubed is 64. Think about what's going to cancel. These 3 A's are gone, and there's 3 left on top. These 3 B's are gone, and there's 18 left on the bottom. So your answer is going to be 125, a to the third, over 64, b to the 18th. And you would reduce 125 and 64 if you could, but there's nothing common to either of those. So that's it. Now B is a little quicker if you remembered what I said to do in the last video, on the last day of class. You could subtract the exponents, x to the negative 3 minus 4, which is x to the negative 7th, but I want it with only positive exponents. So remember what I said to do is circle anything that has a negative exponent on it. So anything that's circled needs to move where it is. So the x to the 4th stays right where it is. Now the x to the cube comes, or x to the 3rd comes down with it. What would be on top? It should have a 1. So this is going to be 1 over, how many x's have we got on the bottom? 7. 1 over x to the 7th, which is the same as x to the negative 7th if you knew that. But especially you'll see today, what we're going to be doing with negative exponents is going to get a little trickier. So doing that circling thing is the way to go. And if you're wondering a random fact of the day, Donald Duck's middle name is Fauntleroy. We had that one already? It sounds familiar to me a little bit. Anyways, let's flip over to today's notes. So hopefully you have a copy of this that you can fill in. If not, maybe write it down on a separate sheet of paper. And let's do some quick practice with negative exponents. So we're going to want to remember the rule that x to the negative n equals 1 over x to the n. And what I told you to really memorize yesterday was that a negative exponent means flip. When I say flip, I mean flip the side of the fraction that it's on. So this first one, we might as well just use the rule that we all know. This is the same as 1 over 2 to the 3rd power, which is 1 over 8. And incidentally, your calculator does know how to deal with negative exponents. So like if I did 2 raised to the negative 3rd, I'd get a decimal, but I can math frac that, and it'll give me 1 over 8. But Obviously, at times there won't be any numbers and you're going to have variables involved, so you need to know how to evaluate these by hand too. Okay, now when we get to more stuff like this, where there's a negative out front or out on the side, you want to think about distributing to every exponent inside. And what did I just put on both of those, that 3 and the 4? I put 1s, because remember that -2 is getting multiplied to both of those exponents. So this is 3 to the -2nd over 4 to the -2nd. Now both of those have negative exponents. So what I would tell you to do is circle both of them and flip the side of the fraction that they're on. So now on top, we're going to have 4 squared, and on the bottom, we're going to have 3 squared. So that's 16 over 9. And again, just to be sure, your calculator can do that as long as you put the parentheses, or use alpha y equals if you have it. This old calculator doesn't. But if I do 3/4 to the -2nd, math bracket, there's your 16/9. All right, maybe give this number 3 a shot. It's the same as number 2. Try not to use your calculator. Put 1s here. So this is 5 to the -3rd over 2 to the -3rd. They both have negative exponents, so I'm going to circle them both. What's on top now? 2 to the 3rd, and 5 to the 3rds on the bottom. So that's 8 over 125. And if you checked it on your calculator, you'd get the exact same thing. Okay, so now let's get into some of these with variables, because this is what you're more likely to see. If you follow these 3 basic steps, you shouldn't have any trouble with these. The first step to dealing with something like this is to distribute any exponents. Sometimes there'll be exponents to distribute, sometimes there won't be. But if there are any on the outside of parentheses, make sure you distribute those first. My second step is just going to say deal with negative exponents. And how you do that is what I've been showing you so far today. Circle anything that has a negative exponent attached to it. Be careful that you don't circle numbers that don't have negative exponents attached. And then you flip the side of the fraction that they're on. And then the third step could actually involve a little bit more work. I'm just going to call it simplify. But really that means if there's stuff that needs to be combined by adding exponents, do that. If you need to cancel some things out, do that. If there's anything to the 0 power, make those 1s. If there's numbers that need to be evaluated, like 5 cubed, do that. That's what simplify means. All right, so let's try some of these. And some of them are a little bit easier, some of them a little bit harder. We'll just see how it goes. So I'll show you how every step works. So when I look at x to the -2nd to the 4th, my first thing says distribute any exponents. Are there any exponents to distribute here? Well, of course. We got this 4. So we're going to multiply the 4 and the -2. So this is x to the -8th. The second step says to deal with negative exponents. So if you know what x to the -8 equals, just write your answer. If you want to circle it and kind of just follow that pattern every time, it is in the top now, so it needs to move to a bottom. So we'd put it 1 over x to the 8th. When there's nothing on top, we put a 1. And that's it. We got it with positive exponents. Number 5, do you see any distributing exponents that we need to do? Nope, no parentheses. But I do have negative exponents to deal with. So I would circle this x to the -2nd, move where it is. So I would first write everything that didn't move. So x to the 4th isn't moving at all. And x to the -2nd, it was on top when I circled it, so it needs to move to the bottom. X squared. There's nothing left on top, so what should I put there? A 1. So now this is 1 over x to the 6th. All right, number 6. Any exponents to distribute? Nope. So deal with negative exponents. There are negative exponents to deal with. What should I do with those? Circle them. But be very careful. A lot of people do that. And what's wrong with that? Well, you circled 36. 36 doesn't have a negative exponent on it. What exponent does it have? It has an exponent of 1. So does 27 down here. So a to the negative 1 can get circled, just like b to the negative third can, but 36 and 27 should not be moving, so don't circle them. Okay, so in your fraction, write what didn't move. We've still got 36. I can drop the 1 at this point. B to the fifth, and I've got 27 a squared. None of those are moving. But what else is on top now? B to the third. And what else is on the bottom? A to the first. Now we're at the simplify step. We can combine the a's and the b's, and then look at the numbers. Can you reduce them? Well, yep. 9 goes into both of those. If I divide a 9 out of here, I'm left with a 4. Divide a 9 out of here, and I'm left with a 3. So my answer's going to start with a 4 on top and a 3 on the bottom. How many b's are on top? 8. So 4b to the 8th on top over 3a to the 3rd on the bottom. There you go. Number 7. You see anything that needs to be distributed? Well, I sure do that -2. So before you do that, put 1s on any exponents that or any variables that don't have exponents, because that -2, remember, is going to the exponents, not the numbers. So this is going to look like 3 to the -2, x to the +4 when we multiply it, y to the -6th, all over 6 to the -2, z to the -2. Okay, what should I do next? I should circle anything that has a negative exponent. So we're going to circle that, we're going to circle that, we're going to circle that, we're going to circle that. So what's not moving? Just that x to the 4th. That gets to stay where it was. Everything else is moving. So with that x to the 4th, we also have a 6 squared and a z squared on top. And on the bottom, I've got a 3 squared and a y to the 6th. Okay, so none of the numbers are going to cancel at all, or the variables, sorry. The variables aren't going to cancel at all. So let's steal the numbers. 6 squared, I really have a 36 on top. So that's 36 x to the 4th z squared. And on the bottom, I have 3 squared, that's 9. So I have 9y to the 6th. That look good? Except for 36 and 9, because 9 is going to cancel out totally. We're still left with 4 here, so I'm going to have 4 x to the 4th z squared all over y to the 6th. So that's where it starts getting a little more complicated, and that's where those steps, distribute, deal with negative, simplify, really start helping. All right, number 8 is dub starred. How come? Well, I have an x to the negative first, so there's nothing to distribute, but if I circle that, what I can't do, don't write this unless you want to make a note of it, this is not 1 over x times x plus 1. Because you can't just move that because of the plus. Plus messes things up. So plus minus messes things up, and we can't flip. So I have to do what x to the negative first really means. What is x to the negative first? Well, using that rule up at the top, x to the negative first is 1 over x to the positive 1. So that's 1 over x. still with a plus 1 next to it, all over x plus 1. You've seen that before. What's that? Did I hear complex fraction? Probably not, but I hope so. It's a complex fraction. So that's where I look at all the mini denominators. Well, x is my only mini denominator here. So I just got to multiply everything by x. Same with everything on the bottom. So we get those to cancel. I've got 1 plus x on top, all over x squared plus x on the bottom. Got to simplify. So 1 plus x is fine on top. I can take a GCF of x out on the bottom, leaving me with x plus 1. Can I cancel? I can cancel pieces that are multiplied. So x plus 1 can go away because there also is an x plus 1 on top. Do I need a negative 1? I actually don't. Why? Because addition is commutative. It doesn't matter if it's 1 plus x or x plus 1. It's the same thing. It's only if this was subtracting in opposite orders that I would need a negative 1. So my answer is x, right? No. Did I trick you? It should be 1 over x because the x is on the bottom. All right, so that last one doesn't come up too often, but I just wanted to show you that because it is a little different. All right, so hopefully you're starting to get the hang of it. There's tons of practice on the homework with that. Let's do one of those kind of wordy problems like I showed you yesterday. Use the properties of exponents to rewrite in the form kx to the n, then evaluate the expression for the given value of x. So basically we want to write it with positive exponents again. So it's mostly the same as what we've been doing. So I first have to simplify that. So what should I do first? Distribute the exponents. This is 2 to the first, x to the first, so now I'm going to have that 9 on top. On the bottom, I'm going to have 2 to the negative third, x to the negative third. Then what? Circle anything with a negative exponent attached to it. So we circle that. We circle that. 9 didn't move, but now there's a 2 to the positive 3 with it, and an x to the positive 3. So we're getting there. Just got to simplify. 2 cubed is 8. So 9 times 8, x to the third. Final answer, 72, x to the third. That's written in the right form. K is 72. We've got the x to the third power. Okay, then it wants us to evaluate it for the given value of x. So we're evaluating it for x equals negative 1/3, it looks like. So this is going to be 72 times negative 1/3 to the third. And I don't really need you to do this by hand. It'd be kind of hard to anyway. You could do it probably. But if I just do 72 times negative 1/3 raised to the third, I get, math bracket, negative 8/3. All good? Any questions? Hopefully not. All right, flip it over. An application of this. Kind of a weird application, but still an application. The folding paper problem. Question, can you fold a piece of notebook paper in half 10 times? How thick will the folded paper be? Will the area of the paper on the top of the folded stack be larger or smaller than a postage stamp? So if you just fold a regular piece of paper, I remember watching a show called Mr. Wizard when I was younger. And if you just take a regular piece of notebook paper, I think the most you can get to fold it is 7 or 8 times. You can try it if you want, but it gets too thick to fold after that. But if we have a less thick paper, like the table below, displaying the thickness of the area of a folded 10 by 10 inch of gold foil that's less thick than regular notebook paper, you actually can fold it more than 6 or 7 times. But what I really want to look at is the exponents here. It says rewrite each of the table entries as a multiple of a power of 2. So if you notice the thickness of the stack, this should make sense. So the first, when there were no folds, this gold foil was 0.28 millionths of a meter thick. Every time you fold it, what happens to the thickness? Well, think about it. If you fold a piece of paper, you're doubling the size of how thick it is. So you're multiplying by 2 every time. And if I keep multiplying by 2, I get the next number. We could write this kind of like a formula. If this is 0.28, if it hasn't been folded at all, then I multiplied it by 2 0 times. 0.56, I started with 0.28 and multiplied it by 2 once. 1.112, I started with 0.28 and I multiplied it by 2 how many times? Twice. And I keep multiplying it by 2 one more time each time. This is 0.28 times 2 to the third. This would be 0.28 times 2 to the fourth. This would be 0.28 times 2 to the fifth. And this, of course, would be 0.28 times 2 to the sixth. If I folded it n times, what would the thickness be? Well, we just made a pattern. And it's 0.28 times 2 to the n, because the number of folds always match the number of times that I multiplied it by 2. So there, I just made a formula. Okay, and the question asked about how big was it? Would it be larger or smaller than a postage stamp? So the original 10 by 10 inch sheet of gold foil in square inches would have been 100, because if it's 10 by 10, 10 times 10 is 100. When I fold it in half, what happens to the area? You multiply by a half. So it gets halved. It gets divided by 2, or multiplied in a half. And every time I fold it again, we multiply by a half again, and again, and again. So the first time it was 100 times 2 to the 0 power because I hadn't folded it at all. But multiplying by a half is the same as writing 2 to the negative first. That means 1 over 2. So if I multiply it by a half again, that'd be 100 times 2 to the negative 2. 1 half times 1 half, 1/4. And then 100 times 2 to the negative 3. 100 times 2 to the negative 4. 100 times 2 to the negative 5. 100 times 2 to the negative 6th. So if there were n folds, what would the area be? It'd be 100 times 2 to the negative n. And incidentally, if I multiply these numbers by the same thing every time, what type of sequence am I making? Geometric. Yeah. These are both geometric sequences. And if you look at the formula for a geometric sequence, they're similar to those. A1 would be like 28 or 100. R value would be 2, or you can think of R as 1/2 in the area one. But anyways, just kind of a fun side fact. So this idea about how much can you fold a piece of paper was actually solved by a high school student in California back in 2001 when I was in high school. Brittany Gallivan was her name. So she became the first person to successfully solve this problem. Brittany first folded a very thin sheet of gold foil in half over 7 times, and then successfully folded an extremely large piece of paper in half 12 times at a local shopping mall. In 2011, students at St. Mark's High School in Massachusetts folded miles and miles of taped together toilet paper in half 13 times. So if people have a lot of time on their hands, try folding some toilet paper. Anyways, Brittany came up with discovering this formula for paper folding, and it looks pretty crazy. We got pi's in it, we got some exponents, but it says this formula determines the minimum length, L, in inches of a long rectangular piece of paper of thickness T needed to fold it in half n times. So if I want to fold something 15 times and I know how thick my paper is, I could use this formula to figure out how long of a piece of paper I would need to get. So here's a question. Toilet paper is approximately 0.002 inches thick. Using the above formula, how long would a continuous sheet of toilet paper have to be to fold it in half 15 times, folding perpendicular to the long edge each time? Round your answer to the nearest tenth of a mile. So it's going to be a pretty long sheet of toilet paper to begin with here. All right, think about where we'd put stuff. It's approximately 0.002 inches thick. So where's that going to go in the formula? T was the thickness. So this is going to go in for T. How long of a sheet of toilet paper would we need? So we're going to be solving for L to fold it in half 15 times. So where's 15 go? That goes for N. All right, so let's evaluate this. We'd have L equals pi times 0.002 over 6 times 2 to the 15th plus 4 times 2 to the 15th minus 1. Looks pretty crazy, but all we got to do is plug it into the calculator. And if you have alpha y equals, I'd suggest using that. Again, this old calculator doesn't really have that, so I'm just going to use some parentheses. I'm going to say parentheses pi times 0.002 divided by 6 times, in parentheses, 2 to the 15th plus 4, and then another parentheses, 2 to the 15th minus 1. And I get that number. So it was 1124522.748. What would the units be? Well, the only units we had here were the thickness. It was in inches. So this is in inches. But I want it in the nearest tenth of a mile. So if that's how many inches there are, how would I get that into feet? Well, there's 12 inches in a foot. So if I divide this by 12, I'd get how many feet that was. So divide it by 12, we get 93,710 feet with some decimals on there. Okay, so that's how many feet. If I wanted that miles, well, there's 5,280 feet in a mile. So we divide this by 5,280, and I'll finally get my miles. So divided by 5,280, and we wanted the nearest tenth of a mile, your toilet paper would have to be 17.7 miles long just to fold it 15 times. Kind of crazy. But if you ever wondered, that's it. All right, that's all I got. So now it's your turn. So here's the homework. It's another worksheet, exponent practice and folding paper problem. Circle those negative exponents. There's some paper folding stuff on the back with that formula from Brit again. Do your best with it, check your answers, and circle any ones that you need help from. Good luck.